So I want you to imagine something. A world where tiny little particles can be in two places at once. A world where going through a solid wall isn't just possible, it's actually happening all the time. Now, this might sound like something straight out of science fiction, right? But it's not. This is the very real and very weird world of quantum physics. Let's dive in.
You know, in our everyday world, things just make sense. If you throw a ball at a wall, what happens? It bounces back. It doesn't just magically pop out on the other side. That's just common sense, right? And that's the comfortable, predictable world we live in. The world of what we call classical physics.
Okay, but what if I told you that when you get down to the tiniest scales, we're talking atoms and electrons, that ball actually does have a chance of appearing on the other side of the wall without ever breaking it? This, my friends, is the quantum world. And its rules are, well, they're bizarre, they're totally counterintuitive, and they are absolutely fascinating. So to really wrap our heads around what's going on, we have to accept this really strange truth. It's like the universe is running on two completely different operating systems at the same time. You've got one set of rules for the big world we can see and touch, and a completely different, much weirder set of rules for the tiny world that everything is made of. So on one side, you've got classical physics. This is the world of planets and cars and baseballs, where everything has a definite place and follows predictable rules. But on the other side, you've got the quantum world. And here, things like electrons aren't just little solid specks. Nope, they're also waves, kind of spread out in space. And this single, totally bizarre idea that something can be a particle and a wave at the exact same time, that is the key to all the weirdness we're about to get into. Now, this idea that everything is a wave, it isn't just some fun little factoid. It's the core concept that shatters all our normal classical intuitions. It's called the de Broglie hypothesis, and it completely rewrote the rules of physics. So back in the 1920s, this brilliant scientist named Louis de Broglie came up with something absolutely revolutionary. He said that it's not just light that behaves like this, but that all moving matter has a wave associated with it. We're talking everything from a tiny electron to a massive baseball. You, me, this entire planet, in a very real sense, we're all waves. So you're probably wondering, why don't I see a wave following a bowling ball down the lane? And that's a great question. It's because its wavelength is just unimaginably tiny, so small it's completely irrelevant to us. But for something as small as an electron, oh man, its wave nature is everything. It stops behaving like a tiny little bullet and starts acting more like a ripple spreading out across a pond. And this wave-like nature, well, it leads directly to one of the most famous and honestly mind-bending rules in all of physics. This is Heisenberg's uncertainty principle. And what's so wild about it is that this isn't about having bad measuring tools or not being careful enough. No, this is a fundamental speed limit on what we can ever know. Because a particle is also a wave, you're forced into a cosmic trade-off. The more you know its exact location, the less you can possibly know about its momentum. You know, where it's going and how fast. Think of it like this, okay? A wide, spread-out wave has a really clear, steady rhythm, right? That rhythm tells you its momentum. But because it's so spread out, where exactly is the particle? It could be anywhere along that wave. Now, if you want to pinpoint its location, you have to kind of squish that wave into a narrow little spike. Great, now you know where it is, but you've totally lost that clear rhythm. Its momentum becomes a complete and utter mystery. It's this cosmic balancing act. You can know where a particle is, or you can know where it's going, but you can never, ever know both perfectly at the same time. The universe itself literally forces a certain level of fundamental fuzziness into reality. It's just how things are. All right, so particles are these fuzzy waves of probability. And this simple fact leads to what I think is the most spectacular, the most unbelievable consequence in all of quantum mechanics. It's a phenomenon that honestly feels like a straight-up magic trick. So, let's go back to our friendly ball and wall. Classically, the ball just doesn't have enough energy to get through that wall. It hits it, it stops, it bounces back, end of story. Simple. But, and this is the big but, remember, a quantum particle isn't just a ball, it's a wave of probability. And while most of that wave gets reflected by the wall, a tiny part of it can actually leak through to the other side. And what that means is there's a small but very real chance that the particle will just, poof, appear on the other side. This is what we call the tunneling effect.
Because the particle's wave of probability extends just a tiny bit into the wall, there's a non-zero chance of finding the particle on the other side. It doesn't break the wall, it doesn't smash through it, it simply appears there. It's not magic, it's just the bizarre but consistent logic of quantum waves.
Okay, so right about now you might be thinking, all right, that's a really neat trick, but is it just some weird theory? And the answer is absolutely not. We have actually harnessed this quantum weirdness to do something that was once thought to be completely impossible.
So how in the world could we possibly use something as strange as a particle passing through a solid barrier? Well, it turns out we use this impossible trick to see the impossible.
We use it to see things we were never meant to see, individual atoms. And we do it with this incredible machine called a scanning tunneling microscope, or an STM for short. It is one of the most powerful imaging tools ever created. And guess what? It runs entirely on this quantum magic trick.
So here's how it works. You take this ridiculously sharp needle, and I mean the tip is literally just 1 atom wide, and you bring it incredibly close to a surface, so close that it almost touches, but not quite. Then, electrons do the impossible. They tunnel across that tiny vacuum gap, jumping from the needle's tip to the surface. This creates a tiny but measurable electric current. And here's the clever part. The amount of current changes depending on the distance. So by scanning the tip back and forth and measuring this tiny tunneling current, the STM can build a map of the surface, atom by individual atom.
And the result? It is absolutely breathtaking. That strange, supposedly impossible quantum trick lets us directly map the atomic landscape of our world. We're not just guessing where the atoms are, we are literally seeing them, one by one. And it's all thanks to quantum tunneling. Think about that. A theory that started as a mind-bending puzzle about waves and particles now lets us see and even move individual atoms. It really makes you wonder, right? If quantum physics let us see the atomic world yesterday, what is it going to let us build with it tomorrow? Quantum computers? Brand new materials we can't even dream of? The weirdness, it seems, is just getting started.